week 6. It's week 6, and I'm just going to go into the main points, just kind of review this week's topics. If there are questions on week 5, I'll look at the forum and see if those are there as well. But let me just, dive right into week 6. Okay. So efficiencies and losses, I don't want to call them the same difference, but they kind of are. Efficiency is always a dimensionless number between 0 and 1. It's a coefficient, it's the quotient of energy out over energy in, and more or less a consequence of the second law. Losses, and you can think of this as energy or power, but in this case we're thinking of as energy power. So losses are going to be, well, I lost 100 megajoules of energy, or I'm losing 10 watts of power. And it's always a difference. So losses are going to be measured in joules or watts. Efficiency is always going to be dimensionless. I'm not going to dive into this thing, but anytime you move something around, you're going to lose a little bit to friction. There is a pumped hydro here in Montana, or there soon will be with the Absaroka Gordon Butte project. Looking forward to seeing that. Okay. So this is still relevant. California is looking for energy storage. And this is obviously dated, but it's still valid for academic purposes. This is an interesting way to look at energy storage, because normally, as we just saw in PV, you normally think of energy storage as being measured in joules, amp hours, etc. Energy storage now is being measured as power. And what that means is that if you have, well, in this case, 1.3 gigawatts of wind or solar suddenly come online, and it's not that out of the question. Last year alone, in the U.S., there were 14 gigawatts of new solar installed. 14 gig, and probably a pretty good fraction of that was in California. We might just make the assumption that 10% of it. So it's like I'm now going to have enough storage to suck all those electrons in at once. So storage is actually rated in watts. It's obviously got some capacity. It's got some energy capacity as well, but the point is it can take that big of a surge. Lovins is great. And I would love to discuss on the forum why the losses add up to 500. Yeah, this guy is the big think on renewable energy. And what he's trying to show here is it's a win-win. So let's look at this. I'm not gonna read the whole thing, but it's naming some pretty big players, DuPont, BP, that actually make money by decarbonizing. This one we remembered from Energy 101. Only 3% of the coal burn actually turns into light. There's the thing on Japan there. This is pretty impressive. He tells this story frequently. He's in Snowmass, Colorado, negative 44 Celsius, frost any day. The house has no conventional heating. So he has just insulated the heck out of his house, is the point. Yeah. Yeah.
Talk about that a lot in green building.
Yeah. Yeah. Oh, okay. Here's the kicker on the energy losses. So if you add 70 plus 9 plus 10 plus 2 plus 25 plus 33 plus 20, you're like, oh my gosh, how did I lose that much energy? Well, you don't add it, you multiply it. So you're losing 70% of 100 here. You're losing 9% of 30 here, et cetera, et cetera. So that question answers itself right there. Okay. And then he dives into the pros and cons of insulation and how he over-insulates. There's a neat little thing on a house. So he talks about transportation, talks about building energy efficiency, talks about just getting off of oil, how the Department of Defense has done that. We looked at Worlo meters this morning, and we still burn 1,000 barrels of oil a second. That's the current rate. 1,000 barrels a second. Which, I mean, it's not that much. 1,000 barrels of oil would fit in this room pretty comfortably. 10 by 10 by 10. Maybe cozy, but they would fit. They would fit. 1,000 a second. He's talking about ultralight cars here. This is also pretty big. Decentralized sources of electricity, and as soon as you put solar panels on your house, you've just decentralized. Oil-free. He talks a little bit about hydrogen. Talks a lot about efficiency. So anyway, Lovins has been way out in front of it for a long time. Okay, this one we won't read it, but the point is this homeowner used his car battery as a means of keeping like his fridge running at the house. Okay, so here's something, this is critical for the assignment. Motors are rated in horsepower, and it refers to the power coming out of the motor mechanically, not the electrical power input. So if it's sending out 100 horsepower of mechanical, more electrical is going to be coming in due to efficiency losses. It also depends on how it's loaded. Is it loaded at high torque, high RPM, et cetera, et cetera. European kilowatts, and again, it's mechanical, not electrical. So right here, we just switched that equation around. So here's efficiency. You know, we could put efficiency over here, put input power over there, and it's the same equation. It's just moving the equation around. All right. Now, the coefficient of performance means that you're putting in electricity and getting heat out. Now, this is always very tricky. This is tricky. So in the case of the coefficient of performance, if that coefficient of performance is more than 100%, all that means is that I've got something hot over here, I've got something I want to heat over here. The something hot could have gotten hot in a number of ways. Someone could have set fire to it, it could have been a solar thermal, it could have been whatever. There's a lot of different ways to make something hot. But if I want to move, let's just say I'm going to move 300 megajoules of heat from the hot side where I don't need it to the cold side where I do, and I only use 100 megajoules of energy to move it, my coefficient of performance is 300. So I'm moving heat. So another good example, these soda can heaters that we've built in the practicum might be rated. So we've got 1,000 watts per square meter coming in. The technology is 2 square meters large. So we've got 2 kilowatts of power, of solar power coming in. And we might just have, gosh, let's just say a 50-watt fan running that guy. So this coefficient of performance, if we're moving 2,000 watts with 50, our coefficient of performance is 40. So, in other words, we're heating, and in this case, the heat actually comes from the sun. There's not a gas flame burning anywhere. There's not an electrical resistance happening. It's just energy coming from the sun. We're using 50 watts to move using 50 watts to move 2 kilowatts. So we divide the 2 kilowatts by the 50, and we get a coefficient of performance of 40. Yeah, it's another good analogy. If you want to use like a water analogy, you might say, well, I've got this this river flowing. In fact, this is a really good analogy. A dam would be another good analogy. So I'm gonna store X feet or X meters of water behind this dam, which is going to relate to, let's say, a few cubic kilometers of water. That represents a certain amount of energy. Well, all I used was the embodied energy in the dam to store it. So your coefficient of performance on a dam can be enormous. And the longer the dam runs, almost the better the coefficient of performance gets, assuming you're not factoring in maintenance and things like that. So. It's a little bit different if you're looking at renewables versus non-renewables. So let's just say, for example, with your solar thermal heater, if all of your heat is coming from the sun and all of your electrical pumping is coming from a photovoltaic, you still have the same coefficient of performance, but it's all renewable. You could also say, well, I'm getting my 200 kilowatts from the sun, but I'm running my fan with a grid tie that's coal. You still have the same coefficient of performance, but it's not as sustainable, I guess, in the long run, because you're using a non-renewable. So coefficient of performance does not refer to renewable versus non-renewable, but that's the way to think of it. It's how much energy does it take to move whatever energy you're moving. So how much sort of service energy for the utility energy is another way to look at it. Okay. Okay, there's a spreadsheet, resources 6. Fill in the blanks with formulas. We'll just leave it the same way it is in problem 1. And I have posted a lot of videos on this. So the fan belt motor system. Give me 1 second, I'm going to pull up some notes on that. So here are my notes on the fan belt motor system. So what I'm writing, these funny little squiggles are actually ADAs. And if you haven't seen this before, ADA is the engineering symbol for efficiency. And I'll show you how to type that if you want to type it in Microsoft Word. It's the symbol. If you start with an H and turn into a symbol, that's the ADA symbol. So the motor has an efficiency, so that's ADA sub M for motor. The belt has an efficiency, so ADA sub B, and the fan has an efficiency, ADA sub F. So in the case of the motor, the electrons pass through the coils, you lose a little bit of heat there. Obviously, the motor's going to vibrate, it's going to make some noise, so you're losing some energy through the motor. In the case of the belt, you have friction, a little bit of noise, so you're losing energy there. In the case of the fan, same thing. As that fan moves, not all of the energy goes exactly where you want it to. So the overall efficiency is the product, we mentioned that before, the product of those three efficiencies. And I think in one of the examples, you might start out with 184 units of energy or power, and by the time the system has had its way with it, you've only got 155 left. So, and the key is that, less comes out than goes in, and you're always multiplying those efficiencies. And, Let's look at problems 1 and 2 here for a second. So this is what it looks like. We can dig into the answers, but next time. But what we're looking at here is that each of these efficiencies is somewhere between 0 and 1, some a little higher than others. Okay, so the another thing that was mentioned is let's say you get this spreadsheet the way you want it. You can take the whole thing, copy it, come over here, and paste it. And it's just Control-C, Control-V. And that's just pretty handy to know, in general. If you're like, oh, I like that, it's not quite right, I don't want to screw it up, here, I'll start fresh. Excel's easy, new tabs are free. So, and I guess that's also something, gosh, I learned pretty early in computer programming, and it's also the reason that Microsoft Windows numbers its operating systems. Windows 10, Windows whatever, because it's never perfect, but that's the best we can do for now, and there it is. So I guess my point there is, once you've reached a place in your worksheet that you're happy with, save it, copy it, move on to a fresh one, because you can always go back to the old one. Don't screw up something that's 90% of the way there, I guess is my point. Okay. All right, so this asks you just to estimate the load for a fridge for 7 days. Should be fairly straightforward. Here's the story. So the gasoline was actually running the house. The battery was there and charged. Don't worry about the other things. A few losses in the engine, a few losses in the electrical components, and there's your energy value per gallon of gasoline.
So you run gas, to run the car, to run this refrigerator and so forth.
Well, he's basically running his car like a generator.
Why don't you just put the stuff out in the snow?
guy might have been,
I guess you don't want to freeze it.
oh, that's a good question. Yeah, why, let's see, where,
Put out the snow.
yeah, why wouldn't you just run that out to the snow? Yeah, I frequently do that. I will, yeah. New England. Well, it was, I mean, I think the reason he used the fridge, let's see, he can run his entire house, the real kilowatt hours of electricity, fridge, freezer, TV, okay, in a few days. Yeah. Yeah, it's more than the fridge. When we drove a Prius to California there in 2013 for the Human Powered Vehicle Challenge, and we used the Prius in the parking lot to run our tools, and we actually had several bicycles come in and pit stop, and we would, do a little bit of maintenance there. So it was kind of fun. We actually ran a pit stop off a Prius in California. Okay, if the refrigerator has a coefficient of performance of 3, compare the refrigeration cooling effect versus the petrol energy input. That's it. Okay. So this one's fairly straightforward. I'm going to see. I think a lot of these old iTunes U are dead. Let me just see how this guy looks. This old Prius question.
Tableau enables everyone in your organization with visual analytics in the cloud. It's powered by IT and fuel.
Okay, so we just finished up problem 1 for week 6, and now we should look into the second one, and it's kind of a Mythbusters problem. It's can you run the fridge for a week? You can go on the nameplate of the fridge too and see how many amps it's running. It's probably on a dedicated circuit. It better not be over 15 or 20 amps or something wrong. This is relatively straightforward. It's going to be 0.9 kilowatt hours. So that was just a quick That's one thing. So that's kind of that's a way to solve it. What I tried not to do in this video is give the whole thing away. Where'd you get that? Oh, duty cycle. Oh, that is fantastic. Okay. Yeah. Okay. So that video is there. There's the Prius problem. Sort of shows the schematic. Okay. Well, don't you love the targeted ads there? What's up, Brenda?
Hey, no, hold on. Carry on, my friend.
Will do.
All right.
Okay.
Tea.
Crumpets and tea coming right up. Oh, and I think this video I actually dug a little bit into the KVAR from a couple weeks ago. Let's just check that out too. Assume efficiency is the engine, and I don't see it given, but it might be as high as 40%. Just straight up carbon efficiency. And then I'm looking at this fridge data, and the duty cycle looks like, well, there's no numbers here, but the duty cycle looks like it might be closer to 30 or 40%. The duty cycle I'm talking about, the duty cycle this is the fridge coming on. So when the fridge kicks on, all of these things spike. The real power, the KVA, and the KVAR all spike. The power factor is actually pretty bad. 50% power factor, not, 50% power factor. It's kind of weird. I'm YouTubing my own YouTube. But what I'm looking at for duty cycle is that the fridge is only on about 30% of the time, maybe 40. And the other thing to keep in mind, since the fridge is a motor, it's got that inductive load, thus it has a relatively high apparent power. And without a power factor correction device on there, without capacitors, it's also got a pretty high KVAR. And I don't think it's really conventional to label it as negative, but anyway, there it is. It's labeled as negative. And when that motor first kicks on, there's a pretty big KVAR spike along with the KVA. So the apparent power and the reactive power both spike. The power factor is off basically when the fridge is off. So if we just kind of look up here and just run straight up, we're always hitting these sort of flat spots. So this flat spot right here on power corresponds with, the fridge was off, so the power factor is 0. You could say, well, is it 1? Since it's not running at 0, well, there it is. Okay. So that was just a question from a previous lecture. So that's pretty straightforward. This isn't that bad. Let's take a look at this guy. Preview quiz now. I'm just going to start the attempt. What's the calculated result of using payment? It's one of these two. I can't remember which. But payment has something to do with the annuity. Maybe annuity value is the best one. Might be all those. Might be all 3 of those. If electrical utility is a 15-minute demand period and kilowatt is a monthly demand. I think that's true. So if you go over that peak once, you get charged. Utility demand period of 30 minutes. 3.8 megawatts. So if we multiply 3.8 megawatts by half an hour, that's 2 kilowatt hours. That's the closest answer, I think. It would be 1.9, but there's 2. A motor's measured amp reading divided by, I'm going to call that the load factor, I think. Full load amperage. So whatever's coming out versus what it's, I think it's the load factor. The current transducer measures let's just take, we'll just do a percentage here. So 180 divided by 115 equals, no, let's do it this way. 115 divided by, no, gosh. Come on. 115 divided by 180 equals 64%. So 64% of the amps are flowing through. And if we take that times 150, 95. Call it 95. Calculate the monthly cost for this electric service. Ooh. Okay, 6 cents a kilowatt hour. So 755,000 times 0.06 equals that seems too high. 755,000 times 0.06 equals 40. Okay, so we're looking at 45,300 for the power, for the electricity. 12 bucks per kilowatt. So let's do, so remember 45, let's see, memory plus. 12 times 1,400 equals memory plus. 35 cents per kVAR. 50% power factor during peak VARs. 50% power factor, so power factor. Just give me a second to calculate that, I can't remember. This guy got a little weird. I'm not sure that kVAR is right, but I came up with kind of a high answer on that one. Motor operates Monday through Friday. What is the use factor? Monday through Friday, 14 hours. So what we're looking at there is so we're going 14 times 5 equals 70 divided by 168 hours in a week, 41. For electric utilities, demand fee is typically, what is the kilowatt of this 48 and 62 amps are measured? All right, it's a 480 volt fan. It's three phase. It'll run at either 230 or 240 depending on how it is wired. What's the kilowatts? So if it's running at if it's wired for 460, its max amps is going to be 87. If it's wired for 230, its max amps are going to be 75. 62 amps times 460 volts. 62 times 460. Let's try it again. 62 times 480. am I coming in low? Should be at 62 amps are measured. Oh, no. Three-phase. Maybe I need to be running the RMS value. I'm just coming in low. Give me a second. Okay, I admit, I'm stumped on that one. I'm not, because we don't know what the size of the transformer is. Okay, 2 more to go. Calculate the monthly cost for the service. Okay, so let's go back to our calculator. 6 times 683,000 equals no, 0.06. Let's do it in dollars. 0.06 times 683,000 equals, so there's 41,000 for your energy. $12 per peak kilowatt. So we're going to do 12. Let's put that in the memory. So 12 times 11 equals the 13K and plus 45 cents per kVAR a month. That's where I'm making a mistake here. So what I was trying to do is start with the kilowatt hours, 65% power factor. Let's maybe just try that. 11 kVAR. Maybe I was calculating kVAR H instead of just kVAR. 65%. So 0.65 and 45 cents per, so 0.45. That's way too high. So this number is too big. We have 11. Let's just have 1100 here. So maybe it's 5, let's try that, 578. 578 M plus 54.7. I think we're in the ballpark there. Okay, so I think I did wrong before. I calculated kVAR on energy instead of power. That's all I did wrong. 54.7. Okay, let's go there. 54.7. Most plant production staff can legally apply an amp probe while a motor is running. I would doubt it. Probably an electrician in there. Okay, finish attempt. See how we did. Answer saved. Submit and finish. How did I do? I normally don't do this, so I don't really know how I did.
It usually gives you,
I can't tell if I got them right or wrong. It's just showing me my answers. I think I did okay, but I don't think I got a perfect score. I think I screwed this one up. Oh, finish review. After it's closed, okay. I won't be able to see the, let's get the right answer. Well, so the right answer won't come on until later. See what kind of grade I got. Am I even in here? That's a bummer. I can't grade myself. All right, well, anyway, I think at least you kind of see how to get through that quiz, so. All right, I think that's it for this week. Do you have any questions on week 5? Do you want to hit something there, or?